Hello and welcome to this video on what are equivalent models. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis and latent class modeling. If this is something that interests you, please consider subscribing to this channel. Also, don't forget to check out the description for additional resources including workshops that I offer through QuantFish. In this video, I want to address an important question in the context of factor analysis and structural equation modeling, and that is the question of equivalence of models. And you'll hopefully see in this presentation why this issue is important and how it can be confusing to people, especially to those who are new to these types of models, and I will show you here what consequences that can have when you have equivalent models. So let's get started and let's look at some concrete models here so we understand the issue better. So I'm going to present this issue based on a very simple structural equation model with two factors, f1 and f2, where factor f1 predicts factor f2. You can see there's an arrow here pointing from f1 to f2, indicating that f2 is regressed on f1, and there's a regression slope coefficient beta 2, 1, and a residual r2, so a variable that characterizes variance in factor f2 that is not explained in the linear regression on factor f1. Furthermore, each factor in this model has two indicators. y1 and y2 are measures of factor f1, and y3 and y4 are measures of f2, and the epsilon variables here are measurement error or unique factor variables. Now, this kind of model you might estimate in the context of structural equation modeling. And so this model is equivalent to a whole bunch of other models, as I will show you here. Now, what does this mean? Equivalence means that there are other models that imply the exact same covariance and or mean structure, if a mean structure is included, as this model, which also then implies that those equivalent models will have an identical fit. So they will give you the same chi-square value for the test of model fit. They'll have the same degrees of freedom. They will result in the same p-value for the chi-square test of model fit, and also the other fit statistics like RMSEA, CFI, TLI, SRMR, and so on. They will all be exactly the same because the models fit the data exactly the same. Yet they may have a very different structure. So they may imply very different hypotheses about how the data came about, so how the data was generated, and therefore this can be highly confusing because you might think, okay, if this model here shows a good fit, if my chi-square looks good, then I can say, oh yeah, this is evidence that f1 is the cause of f2, for example. f1 causes f2 because my model fits well, and so then that's great. However, it can be very easily shown that this latent regression model here has an equivalent counterpart where f2 predicts f1. So you reverse the arrow. Now the beta coefficient is for the prediction of f1 on f2 in a linear regression, and there's a residual r1. The measurement model is the same, so we have the same indicators. And now this model hypothesizes or implies, so to say, that f1 is caused by f2. And this model will fit the exact same as the model on the left-hand side. It fit to the same data set, so you'll get the same chi-square, the same fit statistics, the same residual covariance matrix, residual mean vector if you have a mean structure included. And so there will be no possibility to distinguish between those two models based on model fit. They are equivalent. They're equivalent models. They fit the same data equally well. If one fits, the other fits just as well. So this shows you, for example, or as the first point, that you cannot claim from an adequate model fit that the causal direction that is hypothesized in your model is correct. So that's not correct to assume that. The only thing that you could conclude is if the model does not fit, then that there's something wrong with it. And that might have to do with some causal assumptions that may be incorrect. However, by the fact that a model fits the data, you cannot claim from that the causal direction F1 to F2 or F2 to F1 is the correct one, because these hypotheses are indistinguishable based on this model. Now, this is not the only model on the right here that is equivalent to the model on the left, and I want to show you some additional models so you can see that this issue is actually much broader than just about whether the causal direction is one way or another way in a structural equation model. Another model that the model on the left is equivalent to is a simple confirmatory factor analysis model where the two factors are simply correlated. So instead of having a regression path between F1 and F2 in one or the other direction, this model simply specifies a covariance, a double-headed arrow, and this would be a correlation in the standardized solution between F1 and F2, or it would be a correlation if you set the variances of F1 and F2 to 1, also in the unstandardized solution. And so then this model with only correlated factors also implies the same model fit as the latent regression model on the left-hand side. So you couldn't distinguish a confirmatory factor analysis model from a latent regression model if all the paths in the model and all the correlations in the model are allowed, because in both cases the latent structure is saturated. So the F1 and F2 covariance is modeled here, the variances are modeled, and the means potentially, and this is the case in both of these, and there's no room for any misfit in this type of model with regard to the structural part or the latent variable part of the model in either case. So the confirmatory factor analysis model also would fit just as well as the latent regression model. And moreover, there are other types of confirmatory and other models that again are equivalent to this model. And I want to show you some other examples here. So also equivalent to our initial latent regression model on the left-hand side is this model where you have just a single factor and the error terms for epsilon 3 and epsilon 4 are allowed to correlate. And that might surprise you because this model really has a different structure. So that's maybe more surprising to some people than the fact that an alternative model with two factors where the regressions are specified differently or we have a correlation between the factors is the same, because here in this model you have only one factor. So this is basically the idea here that all four variables measure a common factor, but that y3 and y4 above and beyond this factor have something in common. For example, a shared method effect, a shared item wording effect, a shared rater effect, maybe if y3 and y4 are measures that come from the same type of rating or informant. And so method or indicator specific effects are sometimes modeled with correlated residuals, correlated error terms, and then this model would be, as you would find if you try that out with your data, it would fit exactly the same as the regression model on the left-hand side, yet it makes a very different hypothesis with regard to the data, how the data were generated. And let's go to another example. Also equivalent is a model that looks pretty crazy. So this is called a latent difference score model or a latent change score model, and you might have seen something like that in the context of longitudinal data analysis if you have maybe read books on latent or structural equation modeling of longitudinal data. I have a book on that topic where I show this type of model and other longitudinal models and how they are specified in the Mplus software. And so a latent difference or latent change score model is a popular model for analyzing changes across time in longitudinal studies when you have repeated observations. So in this case, for example, y1 and y2 could be the measurements of, let's say, for example, intelligence at time 1, and then y3 and y4 maybe the measurements, the same measurements of intelligence, the same test again measured at time 2, and then we can look at the difference. So here the factor diff 2 minus 1 indicates the difference, the latent difference or true score difference between time 2 and time 1. So we could model the increase or decrease in intelligence across time with a latent variable. And this is done by specifying the loadings in a specific way. So you can see that here we have y3 and y4 load onto both the f1 factor and the difference factor, and the loadings are the same. So lambda 4,2 for y4 is the same here as lambda y2 here, which is implied by the latent difference model. And then also the first loading is fixed to 1 respectively. And so this makes this factor here a latent difference factor. And now we can regress this difference factor on f1, which is a very different thing compared to what we do in the model on the left-hand side, where we have f1, so that would be intelligence at time 1, and then f2 would be intelligence at time 2, and we're regressing intelligence at time 2 on intelligence at time 1, which is different from regressing the difference score on the initial variable. So this model models something that's very different from the model on the left-hand side. It allows us to look at latent change, latent difference scores, and how the difference, the increase or decrease over time may be predicted by the initial score. So is it the case that individuals who are initially higher, do they change more or less than individuals who are initially lower in terms of intelligence? So that can be modeled here through this regression, which is very different, but this model again is equivalent. This is exactly equivalent statistically, mathematically to the model on the left-hand side, but it allows you to do something different in terms of the latent difference score variable. And then finally, another model that's equivalent to the model on the left-hand side is a so-called method factor model. So in this model, we again have just a common factor, f, that all 4 variables load on. So this would indicate that the 4 measures are really measures of the same construct. Let's say they all measure intelligence. However, y3 and y4 have something specific in common, a method effect. So for example, maybe y3 and y4 are self-rated intelligence, and y1 and y2 are intelligence measures based on an objective intelligence test. And then M would represent the discrepancy between the self-report and the objective intelligence measure. Or y3 and y4 could be measures that have a specific item wording effect in common or something like that, or some other type of method effect. And so this is kind of similar to the model that had correlated errors. However, here we're not modeling this shared method effect between y3 and y4 with correlated error terms, but instead we're modeling that with a method factor m, and that's again equivalent to these other types of models. And so m here is a residual method factor that is uncorrelated with f. So unlike the latent change score model, where the factor f1 and the difference score were allowed to correlate, or where you could specify a regression of the difference factor on the f1 factor, here f and m are not correlated. So they cannot be correlated by definition, because m here is a residual method factor that is not correlated with the f factor. So you can see equivalent models kind of are surprising, because they can have a very different structure and yet fit the same data set, or a given data set exactly the same. They're indistinguishable based on model fit. So you could not distinguish between any of the models that I showed you here based on a chi-square value, because all those chi-square values would be exactly equivalent. If you don't believe that, then take a bunch of data and try it out, and you'll see that all those models fit the same. So you got to be cautious when you specify a structural equation model. You cannot claim from a good fit that this model necessarily is the true model, this model necessarily is the best model for the data. There are other models that fit exactly the same, and they may look very different, or there may be models that look different and that fit even better than your model. So you got to be careful. Really, model fit only serves to rule out wrong models and to tell us something about when something is not right, but you cannot make the claim from a good model fit that this model is the one and only true model. I hope you found this video useful to learn something about equivalent models in factor analysis and structural equation modeling. Please consider subscribing to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.